for the introduction, and I want to thank the organizers for allowing me the time to present to you our current work, and thank you for your patience. So I will be talking about detuning modulated composite pulses for integrated photonic circuits. This is a work that we did in collaboration with Dr. Alica Kioseva from the Bulgarian Academy of Sciences. I will begin with a brief introduction of what is quantum coherent control, and also a little bit on what are composite pulses, talk to you about the coupled waveguide systems within the field of integrated photonics, and also composite pulses in coupled waveguide systems. And I'll just quickly switch this to the other side. There we go. And then this will work. Okay. So quantum coherent control is like a very general field which studies how to achieve accurate and robust state transfer in two or multi-level systems. Let's say if I have a two-level system, as you can see right over here, it can be atomic, molecular, it can be a spin system, or as I will show you in a few slides, it could be a coupled waveguide system. And the methods in which this control is achieved is by means of pulse shaping techniques, or lasers, which is what we have in our lab, and via theories within the title of optimal control or quantum coherent control. So in order to understand what composite pulses are and what exactly do they solve, we'll start with talking about a two-level system, any two-level system with a ground state and an excited state that can be coupled by means of a Rabi frequency. So let's say if I try to excite my system with a laser with a certain frequency, it doesn't have to be the exact frequency of this energy gap between the two levels, and that's how we can introduce a detuning, which is a difference between the two frequencies. And the dynamics of this two-level system is described by the time-dependent Schrödinger equation, and this is pretty much all the math that I have in my slides. So given a resonant, meaning I have no detuning in my system, lossless excitation by a single pulse, which is a function of something called a generalized Rabi frequency, which is also a function of the coupling and the detuning, I can achieve so-called Rabi oscillations. This graph shows that the temporal dynamics of the population of each of the two levels in my two-level system is a function of time, and the time that it takes to create a complete population inversion is a function of this generalized Rabi frequency. But what happens if I have an imperfect configuration? What if I have a little bit of detuning in my system, or maybe the laser that I'm trying to excite my system with is not exact? I can't turn it on for enough time to create this complete population inversion. So given detuning, as an example, the fidelity or the quality of the state transfer decreases. So the solid lines are the one cycle of Rabi flopping, and the dashed lines shows what happens if I have 20% detuning in my system. And to the right, you can see that the transition probability from state 1, the ground state, to the excited state dramatically it loses fidelity the more detuning I have. So one of the many solutions to this problem of loss of fidelity are composite pulses. These are a sequence of pulses with specifically chosen amplitudes and phases that were derived to achieve this complete population inversion. And they compensate for imperfections in the system and imperfections in a single pulse. And they were historically developed in the field of nuclear magnetic resonances. Maybe some of you learned about the Hahn spin echo sequence, but there are many other composite pulses known in this field and other fields today. But what you can see is here that by using composite pulses, historically what you are controlling is the amplitude and the phase of your pulse or of your coupling. But what happens if I have a system that has nothing complex in them, if I don't have any phase that I can control? Okay, and this is where the core part of my talk comes in. So integrated nanophotonics is the field which studies the manipulation of light at the nanoscale. Is meant to solve it's a strong contender to solve the current limitations of electronic devices due to their scalability and on-chip integration capacity. This is a result of Moore's law, which requires the continuous growth of density of electric transistors in, let's say, a chip in order to meet demands for stronger and stronger processing power. So one of the problems with integrated photonic circuits, or just say like silicon on insulator waveguides, which you may all know, is that when we fabricate them with a lot of errors. So if we would like to use these integrated photonic circuits, let's say as a base or as hardware for quantum computation, we can't do that because the fidelity of operations due to these fabrication errors lead to operations that are much lower than the limit for quantum information processing, which states that you cannot have errors that are larger than 10 to the power of -4 of your target state operation. So we wanted to solve this by creating a detuning modulated composite scheme for waveguides. So the first thing I want to do is kind of show you the analog between a two-level system that many of you might have already learned about to a coupled waveguide system. So in any two-level system, you have coupling, detuning, you have a generalized Rabi frequency, and if you want to excite it, you can impinge it with a pulse, and you will get a temporal inversion of the populations. Whereas in a coupled waveguide system, I'm kind of talking about the first waveguide in black here as the ground state. This is where I inject light into it. And since the second waveguide is situated at some sort of distance g away from the first waveguide, the light will couple into the second waveguide after an inversion length. So the pulse here isn't a temporal pulse. It's just due to the geometric coupling between the two waveguides. And the coupling is actually a decaying function of this distance between the two waveguides. I can define a detuning here as the difference between the propagation constants in each of these waveguides. And as the propagation constant is a function of material and geometry, if I have fabrication errors in my two couplers, my two waveguides are not identical, then I will have detuning. And also, I won't go into it, but I can define a Rabi frequency analog that is a function of both the coupling and the detuning. And up here to the top right corner, showing you a simulation of the Rabi oscillations of light intensity in a coupled waveguide system. The power transfer of light between the left and the right waveguide does actually look like Rabi oscillations if I have no detuning, meaning that my two waveguides are identical. And to the right, if I have some detuning in my system, there won't even be any power transfer. All the light will just oscillate in the waveguide that it began in. Maybe a little bit of light will transfer into the right waveguide, but you can't really call it a switch, right? So how can we create a detuning modulated waveguide? So if I have my input waveguide and my output waveguide, what can I control? I can control the fabrication. So I'm just going to show you some examples of what we did over here. So if we keep a constant coupling, and I specifically I calculate the geometry of each composite segment, the difference in the geometry needed in order to create complete population inversion at the output, I can have a very robust coupling scheme. So basically, this is just a recipe for designing a very robust structure to light coupling. Bless you. This is an example of a two-piece detuning modulated coupled waveguide system. This simulation is for silicon on insulator coupled waveguides. They are 340 nanometers in width, 220 nanometers in height. They're situated at a distance of 300 nanometers away from each other. And by calculating the detunings that we wanted to use to achieve this complete light transfer, I saw that the difference in the widths between the first and the second waveguide should be symmetric, and plus 7.5 nanometers and minus 7.5 nanometers on the other side. You can see there's complete light switching after the propagation distance. And at the bottom, I wanted to see what the robustness of this method is. So namely, if I change the target length of each segment by up to 50%, okay, you can see that I have a nice flat line for the fidelity over here, meaning that I can achieve complete population inversion even if I didn't hit the exact length that I wanted. And to the right, you can see that even if I didn't hit the exact target width that I wanted, I can still have a nice robust population transfer. So basically, I insert detuning into my system in a very systematic way that is robust to further errors in the detuning that are inherent in the system. So how did we calculate all these things? So, I'll spare you the gory details of all the theoretical calculations, but it did consist of a lot of math. But what I did want to show you here is that we have like a map of different values, different composite schemes where we can choose the detunings of each of these composite schemes in order to obey robustness to a certain system parameter. So the dark red areas in both what's titled first order and second order composite pulses, doesn't really matter what the difference between them is, the dark red areas are very, very robust to errors in either coupling or detuning. So the vertical line is robust to coupling, the horizontal line is robust to detuning. And since I'll remind you that given a non-resonant system, given a system with detuning, the generalized Rabi frequency is a function of both the coupling and the detuning, and the pulse area, or let's say the length of the waveguides, is a function of this generalized Rabi frequency. If I'm robust to coupling and detuning error, I will be robust to errors in the pulse area as well. So basically we have a scheme that is robust to errors in everything. That matters anyway. So here's a cut line, a few cut lines from these graphs over here that show you that the threshold of admissible errors for quantum information processing, which was 10 to the power of -4, is right over here. And given our new pulses, our first order and second order pulses, we can push the limits of really large errors compared to those of the resonant pulses, which is pretty nice. I also performed calculations for 3-piece detuning modulated coupled waveguides. The upper part is a symmetric scheme, the lower part is an asymmetric scheme, and also for a 4-piece symmetric detuning modulated waveguides. I can go on and on about this forever, but I won't. And we sent our designs 2 months ago to a fabrication facility in China, and we're waiting for the waveguides to arrive to see if the experiment matches our simulations. Hopefully, it will. So to sum up, I showed you the first composite pulse scheme with detuning as the control parameter. No one's ever done it before, and another nice thing is that usually composite pulses, they require 3 ingredient pulses at least in order to perform any operation. And for our composite pulse scheme, we can do it with 2. So that's also a first. I showed you an implementation in waveguides just as an example, but this can work on any 2-level system with either real or complex coupling. So obviously we developed this with real couplings in mind, but it can be used for anything. So if you have any ideas for a system that you would like to couple in a robust and efficient way, let me know. I'll be happy to hear. And it's robust to errors in coupling, detuning, and pulse area. I would like to thank my advisor and Dr. Elitza Kioseva for their support and advice on this work, my whole group members, and I would like to thank you for your time. Let's have coffee.